Okay, thank you, Nathan. Hello, everyone attending this. Just another thing I would like to point out: if you have anything that you don't understand, please post a question, and then Nathan will put it in, or will flag it, so that we don't leave anyone behind. So I don't want people to, from slide 3, not understand something and then arrive at the end without being able to follow the rest. So please let me know. Something about me: I work at DIgSILENT as electrical engineer since 2018. I worked in many different places before, but this is where I am at the moment. We do the following. We are a consultancy, and we specialize in generators testing, connection studies, and software and monitoring. So we sell Power Factory and assist users with the Power Factory software. We also do some international work, mostly network expansion and training for power system or for using the Power Factory. And we do power quality, both as part of connection studies and in case there are issues, people ask me questions and so on. So these are the topics we are going to cover today. So you're watching there, and I get this. So what is a distorted waveform? We start from the very basics. So if people know it already, great. If everyone knows it already, maybe you can tell me, look, we know this, and then I will speed up. But if you don't understand something, please ask. And we will go through what power quality issues are in general. When we talk about power quality, what is the power quality? And as a subset of power quality, we will cover what harmonic distortion is. And then see how it propagates into the grid. We will have a look at the harmonic models, which are the tools to represent a real device into a circuit and to replicate into that circuit the effects that it has on distortion. Then, given that we want power to be of quality, to be good, how much distortion is too much? So how much can my equipment take? How bad quality power can my equipment take without failing? And then we will talk about measuring this distortion and how to mitigate it, because as we understood, we don't want it, so we want to get rid of it. How do we do that? So to start, this is a distorted waveform. I measured it at my house. I don't remember what was on while this was happening, but as you can see, the voltage at my connection to the distribution is a flat top, is not a sinusoid. The current is very far from being a sinusoid. So how do we say that power is distorted, that there is bad power quality? Because the waveforms, when we look at them, they're not sinusoidal. So, however, there are power quality issues that make the waveform non-sinusoidal every now and then, and other ones that are periodic. So if we look at this picture, we can tell that that sine wave is periodical, is non-sinusoidal, but every period, every 20 milliseconds, which I did something wrong with the time axis, apologize. It looks like we are running at 25 hertz here because it's 40 milliseconds for a period. No, I got the time axis wrong, sorry. But over a period, the next period, you can tell it is the same. So there is something that is periodic, and this we call it harmonic distortion. So we can have a look here at what power quality is about. Having sinusoidal voltage waveforms. Otherwise, we get energy at different frequencies that causes, for example, heating and PLL malfunctioning and many other issues. We will cover them in detail later. We want a constant frequency. Otherwise, things don't maintain a constant speed. No interruptions. Otherwise, your computer may reset. We don't want voltage to sag or swell because things may trip on under or over voltage or on over current if it sags too much. We don't want spikes because are bad for the insulation and for the capacitor. Out of all these, the phenomena that usually are sporadic are all of them, apart from the voltage waveform not being sinusoidal in a periodic fashion. So the objective is to estimate or measure the level of energy at frequencies different than, for example, 50 Hertz. Here in Australia is 50, in the US is 60, to make sure it's not excessive. So we are talking about a distortion which is periodic. So every period, the shape is as bad as you want, but is always the same. So we use something to analyze some periodic signal, and this is the Fourier transform, periodic or periodic enough. But this is very important because if you apply Fourier transform to something that is not periodic, you get phantoms, you get results that are, you need to know that you're not supposed to do that and that your results may be very approximative. So this is a key point to remember. Use the right tool for the right signal that you want to look at. So analysis tools, we have the Fourier transform. Brief overview for whoever may need to review it. How do we do that in brief? We get a window of waveform samples. A window means, for example, 0.1 second, 5 periods at 50 Hertz or thereabouts, depending on the frequency. Say that we have n samples at sampling frequency f, for example, 1 kilohertz. The duration of the window is the number of samples divided by the frequency. So sampling frequency 1 kilohertz, so 1000. Number of samples, we have, say, 1000 samples. T is 1 second. That would be 50 periods, for example. Then we get that, we decide that, we do a DFT on that, and we get an equal number of points, of which half are positive frequencies, half negative frequencies, according to how we set it up. Or it can be mirrored at the maximum frequency. What is the maximum frequency you can represent? Half the sampling frequency in conditions where there is zero noise. That's a theoretical maximum. So in this case, we sample at 1 kilohertz. Maximum frequency we can represent is 500 hertz. And that is 500 hertz divided by 50 hertz is the 10th harmonic. So it's the 10th multiple of the base frequency. Sorry, of the 50 hertz. The base frequency, what we call frequency bin, is f, sampling frequency, divided by the number of samples. With our example, 1 kilohertz, say 1000 sample, so 1000 hertz divided by 1000 means 1 hertz. So our bin is 1 hertz. So our components for the signal will be constant, the average, DC, what we call DC component, then 1 hertz, 2 hertz, 3 hertz, all the way up to 500 hertz. As you can tell, we will have 1000 points. The DFT doesn't lose any information. You can do the DFT and then do inverse DFT, you get the same signal. You don't lose any information. It's not like doing an MP3 file that you do your recording, compress it in MP3, you can't decompress it and get the same one because it's a lossy compression. There is no loss, there is no change in information. Then what do we do with these phasors? Because they are complex numbers. They have an amplitude and a phase. The phase, we don't use it much. The amplitude is what most of the time we look at, and we use it for measuring the distortion. To get the exact picture of how this gets done and measured, please check out those two standards, those two IEC standards that I mentioned. Then if you're going to get a copy of the presentation, I guess you will be able to read it in detail. So now again, how do we use the phasors? they function exactly like they do at 50 Hertz. We have current sources, voltage sources, and impedances, but not only at 50 Hertz, at all the harmonic frequencies of the 50 Hertz, or if we want, at each bin. Usually we look at the harmonics because usually the interharmonics, so whatever is in between, say 50 and 100 Hertz or 500 and 550 Hertz, we usually don't look at. But there could be energy there. Usually there isn't much. So current source is a current in a branch of a circuit that does not depend on the voltage. Please remember, we are talking about a certain frequency. Voltage source is a voltage that does not depend on the current at that frequency in between two nodes. And harmonic impedance is the same as the 50 Hertz impedance, but at a different frequency. So not much mystery here. So we are asking, so what are the sources of this distortion? What makes a waveform from a sinusoid become like this? It can be many things. For example, saturation in a transformer. It would be nice to go into the detail of everything, but it's only 1 hour. So if you have questions, you can ask me, or I can point you to good reads and so on. It's not something that is immediate and can be covered like this. So I will just mention them and then you can look up, and there is heaps of it on the internet. Transformer saturation, anything with power electronics. The old incandescent light bulbs, believe it or not, they are non-linear load because the resistance of the filament, now we don't have them anymore, but it changes with the voltage. So when it's hot, so peak of the voltage, when it's hot, has higher resistance, so the current comes down. When the voltage goes down, it cools down a bit, resistance decreases, and so you do not have a constant current, and is non-linear, this effect with the temperature. But now no more, because everything has got probably an electronic, so we fall in the other category, like an LED lamp has got a little either flyback converter or whatever inside. Arc furnaces, they are used. Yes, they create lots of harmonics. And motors, if they have, especially if they have an electronic controller, so almost everything gives harmonics. Sinks, what absorbs these components that are not at 50 Hertz? Where do they tend to go in? In the power electronics, I say, believe it or not, because we said it's a source, but it does also have a filter in front of it. So remember, when you connect to a grid, it's not my fault, your fault. It's not like having the fence and that's your neighbor and this is my neighbor. It's all interconnected. So if you are causing distortion, maybe you are also filtering some of your distortions and the distortion of someone else if you have something to decrease your own distortion. So it's all in common. So you cannot cut there and say, this is mine, this is yours, because it creates a big circuit. So they are in these kind of separations. Motors and generators, they do absorb them, mainly at lower harmonics. Capacitance in the lines and cables, capacitor banks, mainly at higher harmonics because its impedance decreases, and so more harmonic current will flow through capacitance. If you put a capacitor and look at the current, will look much more distorted than if you put a resistor of equivalent impedance in absolute value. Why? Because that impedance changes with frequency. So capacitor, if there are high frequency harmonics, they're going to cop them all. That's why often they fail. They are one of the main indicators of too many harmonics, too much distortion in your system, because they tend to take them. Harmonic filters, which are devices built to sync harmonic components, and anything with a frequency-dependent loss that increases with frequency. For example, impedance of conductors increases with frequency. So the resistance of the conductor in your transformer, transmission line, your motor, your generator increases with frequency. So if there are currents at higher frequency, there will be more resistance and so more losses. So that current will get, that energy will tend to it will be more likely that that energy at higher frequency gets dispersed in heat. So your grid looks, we can say, more resistive at higher frequencies because of this phenomenon of frequency-dependent losses, also called eddy currents. Again, I don't have time to explain in detail, but you can, there's lots on the internet again also on this. Again, sources on propagation, where are the sources? So here, what are the sources? Here, where are they? Everywhere. There isn't anyone that is sort of without any, generating any. In your house, heaps of them. Get yourself an oscilloscope with a current clamp and have a look at your microwave current. You wouldn't even say that is absorbing anything at 50 hertz. It's truly bad. The oven, no, that's the best because it's a big resistor that doesn't change much in temperature. It's quite nice and replicates the voltage. It's very good approximation of a resistor. Any factory that has connection with distribution grid would absorb harmonics, would create harmonics, transformer magnetization current. If you increase the voltage, they absorb current which is distorted because of the saturation, so they do contribute. In a power station, the house load, for example, you have a big power station, it would have, maybe if your power station is 400 megawatt, it may have 20 megawatt to actually run the place for all the motors, pumps, and everything. And lots of that has got variable speed drives, rectifiers, you name it. So it may be a source of harmonics. And inverter-based generators like PV or solar farm, wind farm, whatever has got power electronics. Maybe the only part of the grid that does not create distortion is the transmission lines. They may create negative sequence stuff because of unbalance, but they do not create distortion. How do they propagate? Same way at 50 hertz, but devices do not behave in the same way. So we need what is called a harmonic model. So something that we can put in a circuit at another frequency, at a different frequency from 50 hertz that predicts the behavior at that frequency. Again, we are talking about periodic distortion, so it's not a dynamic model. It is a model static as 50 hertz, but not at 50, at 250 hertz. So we are talking still phasors. There is no dynamic models here. So because we need to estimate the level of distortion, what we do is get the harmonic models of what is involved, as we described them before, get point 2, the level of the sources. How much distortion do they introduce, each source? And then some method to combine the effect of every single source. Some methods are proposed in IC 61036. That is the standard where we have these methods described, proposed. There are other ways. SIGRE has got lots of documentation on that. You can find it on the site, and if you're a member, I think you can download it. I'm not an expert on that, but there is lots of good documentation on SIGRE website talking about distortion, really, and it's worth reading. It's a long thing to read. They can be difficult, but they are a very good reference. So as I said here, the best ingredients don't necessarily make a nice meal unless you combine them properly. What does that mean? That if you get fantastic harmonic models and you put all the bells and whistles on them and they are very detailed and so on, if you do not put them together properly, they will not give you a good estimate of what the distortion is. So a good model is as useful as how good is the way you put it together in a circuit with all the other models. So attention must be paid to how we combine things and what method we use for the calculation. That's why I always recommend measurements to check how do the model and how does your big model of your grid, for example, compare to reality. Are you getting an okay estimate of what is happening or is completely out. Then once you get that, you know that your big model with all your little models interconnected has got is close to reality. And then you have to estimate the uncertainty of your results. So models are an approximation. The combination of models in a grid model is a much bigger approximation. And also the combination of the effect of every single source is an even bigger approximation. So we can't escape from that. So the correct thing is not to aim for perfection, but is with whatever you can achieve, estimate the uncertainty of what you have and see if it is fit for purpose. So if you want more, if you want less uncertainty, then you know what the sources of uncertainty are, and you can go and try and address it. But if you say, I cannot address this, then that's it. There is no use taking those results for something which is better than what in reality is. That needs to be accepted as good engineering practice. Now, we look at the effects on the equipment. What do harmonics, what effect do they have? We have to remember that the principle here is that the grid functions with imposed voltage. So ideally it is a voltage source. So you want the voltage to remain the same, to have your 50 Hertz and nothing at any other frequency. Why? Because things are built to receive a pure 50 Hertz without distortion voltage. So the sources, we talk about harmonic sources injecting a harmonic current. Why? Because our system is assumed to be a voltage source. That's the ideal way of having it functioning. Fixed frequency, fixed voltage, and no influence from the harmonics. So it's not sensitive. So you inject current at 250 Hertz. Do you find a voltage at 250 Hertz? No, because it is a voltage source at 250 Hertz with zero voltage. It's a short circuit. No matter how much current you put in at that frequency, you will see no voltage. Why? So that the voltage remains clean for everyone. That is the objective, ideally. In reality, it doesn't happen. So what are the effects of this not happening? You can get, for example, a 415 like a normal industrial supplying household. If you have three-phase, your neutral will get hot. I cannot go into the details of why, but you can look it up or we can discuss later. Motors, even harmonics, make them get hot, and generators. Conductors in machine, as we said, get hot due to the skin effect and the eddy currents. You get high current in capacitors, as we said. Insulation degrades, especially with high currents, with high harmonics. Why? Because capacitance allows high frequency to go through. The higher the frequency, the lower the impedance, so the more current. So the insulation will take lots of capacitive current at very high frequency. And vibrations due to torque harmonics in motor. Again, big topic, but no time here. But this is more or less what you get. This is the harm done by harmonics. Most of this is capacitors dying and things getting hot. That's most of the thing. So the point then is, okay, this is what happens, but how much distortion is too much? How much distortion can equipment take? We cannot really, we can look for these signs, heating, capacitors failing and all that, but you don't wait for it to happen to say, oh, I'm distorting too much, because that's too late. You're already breaking things. That's not good practice. So, and also usually the larger the device, the smaller the margin. So you can mistreat a 500 kVA transformer much more than you can mistreat a 500 MVA transformer. Way more in terms of, in proportion to its size, the bigger the machine, the more delicate it is. Because given the cost, you cannot oversize things too much. So everything is built on tight margins. You get out of those margins and you are done. So that is in general the thing. How to establish generic limits then? We do need to aim for a certain level of distortion that is going to be safe for our devices. So that's a necessity. We cannot look at every single device and say you can get this much, you can get this much. So collectively, what is a safe value that we can aim for? There are proposed values in IEC 61036 based on industry experience. However, they are old, set many years ago for a landscape, electrical landscape, let's call it, that changed a lot. There were lots of rectifiers, lots of thyristors. Now things have changed. Those things are on the way out, and the inverter, variable speed drives, and all the stuff is on the way in, so things are changing. There is lots of work being done, also within SIGRE, within IEEE, and so on, in the engineering community in general, to come up with updated values. But those that everyone agreed on, and then that they came into that technical report, it is not a standard, it's a technical report, 61036, are those ones that we all agreed on, so we are still using those. However, everyone is urged to get into it and contribute to checking whether they are still good or we need to update, because the grid and power systems in general are changing fast and are changing a lot. So we need to update our common understanding. So we do have these planning levels and compatibility limits. Planning levels is what I was saying, the aim towards which we can decide to maintain distortion, around which we can maintain distortion for everything to be reasonably safe. For harmonics not to be trouble, we have to aim at a distortion which is in the planning levels. The higher the voltage, the lower the distortion, usually, for the reasons that I explained before. A small piece of equipment can take a bad waveform. You know, here, this is at my house. I have a voltage like this. Nothing is happening to my equipment. It's not that things are failing, catching fire, and so on. You put a voltage with this shape on the 275, for example, kilovolt grid, and you will get trouble, seriously. So it is different. So the higher the voltage, the much cleaner, the much more ideal things have to be. Hence, these compatibility limits and planning levels get higher at lower voltages in general. And the compatibility limits is what everything must be able to put up with, basically, in terms of electromagnetic compatibility. So they need to be compatible with these limits, with these values of distortion in the supply without failing. Again, the higher the voltage, the lower this limit become, and above a certain voltage, they are not defined. Why? For the reasons that I explained. The bigger the equipment, the smaller the margin. When something is very big and very expensive, you ask the manufacturer how much it can take. I'll try to be quick because I think I don't have much time for the questions. About measurement. This is something I keep banging on. It is very important to measure because it shows us how things are going and gives us understanding of what is happening. As an engineer, yes, you have a computer and everything and the calculations, but you do need to get a feeling for things as well. We are humans and we function with getting a feel for things on top of the calculation. A feel meaning that usually it is like this, but now it is different. Why is it different? That's a feeling. That's not a scientific, that's not a calculation. So, and it is important that also to see how things are going, how things are changing. As I say, one needs to trend things and develop a connection with what is happening, also with harmonic distortion. How do we do that? We measure. And how do we measure? The testing and measurement techniques and the power quality methods are in these two standards. I will not go into the details, but you can read them. Also to understand how your instruments function, because they are built according to these standards. So if you understand how they function inside, then you will be able to use them properly. You will be able to understand what to expect from them. As I say here, how measurements provided by commercially available instruments are generated and their limitations and the meaning. So can you expect 0.001% to make any sense? No. Why? Because you know the uncertainty of your instrument and the uncertainty of your process, for example, of your measurement process. Now, let's have a look at that. I promise this is lots of information, but I hope that you will be able to get a copy of the presentation, and then I'm available for questions and whatnot if you have anything in particular. So what is measurement uncertainty is an estimate of how wrong your measurement is. Basically, what is a wrong measurement? There is the true value, which is a philosophical idea. So does it exist or not? Even we can discuss that, not now, but does it exist a value which is with zero uncertainty? Yes, when you assume it, like speed of light, ST5, one of the constants in nature is a constant. So you assume that as a constant and then build everything on it. Permeability of vacuum, again, that's a constant. So those have zero uncertainty. Your measurement doesn't. So there are various types of uncertainty, from systematic causes, type A, from causes that cannot be identified specifically, we call it type B. And all this is explained in this document, Guide to Expression of Uncertainty Measurement. Again, it is a heavy read, but please have a look to understand. And there are also other documents and other resources all over the internet to understand metrology. It is important because even if it's difficult to do it, you cannot get a number out of the computer, out of the measurement instruments, and just don't pay attention to the uncertainty of that and use it for what it is. That is wrong. Because if you make decisions that also cost money, whether something is okay or is not okay, compliant, non-compliant, whatever it is, based on that number, you are making decisions that in reality may cost people time and money. So are you able to make a black and white decision, or that number has got an uncertainty which is too high to say this is good, this is bad? This is very important because it brings things in perspective and ultimately gives you more understanding, not less understanding. If you know the uncertainty of what you are doing, of your measurements, you understand more about what you're looking at than by taking the numbers as they are. To do that, you have to look at the measurement chain. This is just an example. We have a HV bus, we connect a VT voltage transformer to measure, and then we have a connection to a meter, and then we use an algorithm, calculation process, to see if the plant is, for example, compliant or not with the distortion level that we set. Say you cannot contribute more than this. But what is the uncertainty of the number that gets calculated through the measurement and our calculation process? Can we say that that number is above or below the threshold? With what? How confident are we that is truly above or truly below? What is the probability that is above, the probability that is below? We need to get some statistics into this, and we need to estimate, first understand what the sources of uncertainty are, and then estimate the uncertainty. Again, it is an estimate, it's not perfect, but it's better than taking digits bluntly and comparing them and say, no, it's above. Well, wait a second, like, is it always above? Is it for sure 100% that is above? Or So VT, there is no linearity over frequency. No VT is certified and tested for any frequency other than 50 Hertz. If you use it at 2000 hertz, that's a leap of faith. No one ever checked that. If you checked it, good on you, that's fantastic, but it's not on the label. You don't buy them to measure at 2000 hertz, not a normal VT. So most of the time is a leap of faith. Again, that should be checked. Effect of the burden on it, burden at the VA of your VT, okay, at 50 hertz, at 2.5 kilohertz, what is an okay burden? Again, mystery, let's look into that. Connection to your instrument. Your instrument has a high impedance input. It's likely that your connection, your cable that runs through like 10 bays of a switch gear is going to pick up lots of noise at high frequency. If we say that there is a harmonic at, I don't know, 2000 hertz again, is it picking up noise or is it truly there? We have to be careful. Your meter uses certain algorithms and has got a discretization error and so on. Again, standards IEC 61047 and 430, it's all in there. What is the error coming from that? Then you do data processing to understand your contribution, for example, using the subtraction of production distortion less background measured the month before. What is the answer? Is not wrong, is not right. What is the uncertainty of this process? We have to look at the uncertainty of, for example, the background that you are measuring, meaning what is, how good a predictor the background of 1 month before is of the background now. It's a predictor, yes, but how good is it? Let's attach an uncertainty to it, plug it into our data processing, find through what is written in this document, Guide to the Expression of Uncertainty Measurement, how to do that. I cannot explain it now. And we can estimate, we can calculate a contributed distortion through our process and estimate the uncertainty associated with it. And then we have a figure that we are confident in, that we can use because we know how wrong we are likely to be. So that puts you in a much better engineering position. At least that's that's how I feel. Second last slide. Mitigating harmonic distortion. Well, that's the objective that we all have. How do we do it? We eliminate the sources. It's not always possible because we do need an inverter. We can't do without. Or we increase the capability of equipment to withstand distortion. So things ideally will put up with anything you throw at them. Again, not practical because it will cost lots of money. So midway, we introduce filters. What is a filter? A device that is built to absorb harmonics. So create a low impedance, a low shunt impedance at higher frequencies so that the voltage doesn't change much. Why? Because the impedance is high. This can be a topic for hours and hours of discussion, but just one thing I want as a takeaway, that a bigger filter does not mean less distortion, not necessarily. If you have lots of distortion, if you put a humongous filter, you may find yourself with more problems than what you had before. It's like a medicine, you need the right dose. Okay, not that twice the medicine you heal in half the time. It's not like that. But I leave this for the moment. A few points to remember. It's just like a little summary and a little bit of wisdom I'm dishing out. Harmonic distortion is a periodic thing. If you want to look at other phenomena, don't use Fourier transform. Look at another tool. There are many. Again, I can't discuss it here. First, understand what is happening in reality, then try to make sensible models that are not too complicated. Why? So you can have control over them. If you have to choose 20 parameters, is way more likely that you make mistake than if you have to change 2. So again, less is more. So 2 parameters chosen carefully are much better than 20 parameters plugged in just because. measure as much as possible and anywhere possible, so you get a feeling for what is happening. Truly, looking at measurements give you a reality check, and often makes your convictions, breaks your convictions, and causes more doubts than when you than what you had when you started measuring. But it's better to, you know, get a reality check before you build up a whole reasoning or a whole economical technical decision based on your preconcept idea, because you haven't measured. So measure, 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 and understand limitations of your instruments and the uncertainty of your measurements. That is very important. Trend over time to see what is happening and correlate with what is happening in a grid, for example. So I connected this. What did distortion do? Did it go up? Did it go down? Nothing happened. That is important as well. IEC 61036, it is a sensible technical report, but is not a law. So people do not have to follow that. It is written in the standard. We call it standard, but it's called technical report in the title. And then ask yourself, what is the consequence of a harmonic distortion level going over a limit? Always ask the what if question. So if I have 0.5% and my limit, I set it as 0.4%. Is it going to be a disaster? What was the uncertainty on my limit? What is the uncertainty of the estimated level? How do they overlap, these two, let's say, Gaussian curves? Do they completely overlap in the sense that it's okay, even if it's a bit above? So we need to reason this way. For power quality, especially for harmonics, is not really possible to go black and white. And then at the end, don't be afraid if the measurements do not match the models, but quantify your approximation. Look at the uncertainty and see if it is okay or not, if you can work with that or not. I am done. Thanks for listening. I wanted to finish earlier, but we have 10 minutes. I thought I would be faster, but it was a lot. Thanks everyone for your attention. And if you have questions, please ask, and also contact me if you want later. Thank you very much.
Excellent. Thank you, Umberto. A very knowledgeable presentation, so thank you for the time. We do have a good few questions, so I'll try and run through them in the 10 minutes that we've got left. First one, I'll copy them into the chat. So the Q&A, for anyone who wasn't aware, wasn't working properly. So we've set up quickly a Slido. So if you haven't seen that or haven't added any questions, then please follow the link in the chat, jump on over and either add a question or vote on one.
No, what did I have to do? Do I have to look at them written somewhere or?
You don't. I'm going to copy them into the chat so you can see them more easily. So
Okay,
the first one is, given the over-pessimistic approach to the harmonic assessments in the NEM, are we not risking having any excessive number of harmonic filters in the network?
Yeah. Well, that can happen. Yes, there isn't really pessimistic or optimistic, or depends on the point of view. If you are a network provider, you just want everything to be safe, and you safe in terms of what you are providing to your clients as a waveform, in terms of how clean it is, and you do not want trouble with things malfunctioning. My feeling personally is yes, there are too many filters, more than too many. I think that many times they are placed in the in the wrong spot. This is a huge discussion that is going on at the moment, and yeah, there needs to be work done on how we are putting them. But again, there are lots of questions. I would really like to talk about this further, but I think the wise thing to do is to see what perspective, like if you are a network provider, or if you are a generator, and if you are a user, like household. Let's have a look at it from these three perspectives and see where we should put the filters, and how we can get this to work well for everyone. That's all for now. I don't want to take more time I can't. I would like to, but I can't.
Okay. Thank you. Moving on to the next one. Do you think that the NER is keeping pace with the standards and the general progression of understanding of power system harmonics? And if not, how can it improve?
Yeah, I think it can improve. It again pace with the standards. They aren't real standards. There is that's a technical report that became a standard in Australia, but is copy paste of the same text, and now it is a standard. It is not. It doesn't impose anything. However, it is the only set of values that looks most like a standard, so we are using it. I'm not saying it's wrong, but improvement can be done, number one, through measurement and trending. So we have to have a look at what is happening. Things are changing, they are changing fast. Are we keeping track of the distortion? Are we keeping track of the effect of these changes? I don't think so. I think this is the main mistake, is that we are using documents and processes and wisdom developed many years ago for the situation back then, and trying to apply it to a situation which is not only different, but changing very quickly. Plus, we are doing this without looking at the effect of these changes. So please, I always repeat, we should measure and trend distortion and have a look at where it's going. Is it going up to the stars? Do we have to worry about anything happening? And let's make this public. We don't have to name and shame this node, that distribution provider at the bulk connection point injecting all this distortion, this generator doing this and that. But in general, there can be information for everyone. Like, do we have, as engineering community, do we have to worry about this? And if we do, which way is it going? What is happening? So where do we have to spend money to fix this? I think this is what is not happening in general. So that's we can't really even create better standards unless we look at what the situation is. What do we need? That's it. Thank you.
Thank you, Umberto. Okay, next one on the list. If you're familiar, can you provide any comment on the pros or cons of the different assessment methods used by different network service providers, or that different network service providers require us to use?
Well, I'm not completely familiar exactly with what everyone does. I understand Transgrid does the validation of the harmonic model of a plant, which is a very sensible thing to do, in my opinion. And that is, it is very good. And sometimes I participated to it for one plant and so on. And yeah, we realized that the model provided by the inverter manufacturer had some inaccuracies, and we got what we did the process independently, and we got to similar results. So I think that more of this should be done. PowerLink approach, I think, is essentially in line with IEC 61036. In general, what they are okay, both processes. What I would do is try to validate the polygons. It is difficult to do, but at least see if we can get some points and see if they are okay, because we are basing pass-fail and decisions that are for lots of money based on a model which is a harmonic model of the grid, which is not verified. It's very difficult to verify it. In some instances, it needs to be taken for what it is, but there are ways that can be applied to try and see how correct it is. And I think more of this should be done. In general, I think that all network providers are trying to do their best to apply the same process in a fair way across everyone who is connecting, and that is a necessity in their position. Hence, altogether, we have to come up with another method or set of methods that we all agree on that is going to help both sides. I think this is really the way we need to go. Thank you. So what types of loads are less impacted by harmonics on their performance? I would say anything in your house. Small appliances, as I said, are the least sensitive ones. I'm not saying that you can supply them with a camping inverter with a square wave and nothing is going to happen, especially if they have capacitors, like a little filter in there before the, for example, a flyback converter for your wall wart, for your little transformer. Maybe that will shorten their life. I would say these ones are the ones that would suffer less. Anything that is inside your house, anything that is connected to the power grid, very big, very expensive stuff. It's not very big and almighty and robust. Is very delicate. It sounds stupid, but the bigger they are, the more delicate they are. Thank you. Next.
Next one, are there particular orders of harmonics that are more impactful than others?
Well, it depends on what device you are looking at. If you are looking at your 415 board, the odd harmonics, the triplet harmonics, so 3, 6, 9, and so on, will flow in the neutral. So if you see a hot neutral and you measure all your loads and you say, look, here everything is balanced, you measure your currents, they look balanced. What the hell is this neutral getting hot? Is because these harmonics are the zero sequence and flow in the neutral. So these ones are bad for that. Even harmonics for motors and generators. Why? Because they cause a magnetic field at the stator that rotates the other way. So it literally acts as a brake and heats them up. So that's what can happen. Very high orders, they can be bad for insulation. They need to be bad though. So what I'm saying is that is not a 0.1% is going to destroy things before your eyes. They need to be there in quite a substantial amount, like depending again on the size, but for some big piece of equipment, 2-3%, you start seeing bad effects. For something smaller, like in your house, 10%. Maybe, like, have you seen the waveform in my house? I don't have fire coming out of my appliances. So if you apply that voltage, everything keeps functioning more or less happily. It is built also to put up with that amount of distortion. So that's, yeah, that's it.
Excellent. That is unfortunately the last question that we're going to have time to answer.
Yeah.
Thank you very much, Umberto.
No problem.
Just as a little bit of a summary, what we will be doing after this, Umberto's mentioned being comfortable with sharing in the slides, so we will upload them to the KMS system and send out a link with where they are located. So anyone who has attended the presentation and is an NGM member will be able to access those slides and can email any additional questions through that they may have. And we'll also try and spend a bit of time to address any questions that we didn't manage to get to and upload them in the same place. So thank you very much again, Umberto, for the time today, for running us through the background on harmonics and power quality in general. It's been very enlightening, and I know that myself and a lot of others will have learned a lot from this. So thank you. Thank you again.
Okay, thanks everyone. Bye-bye.
Thank you, everyone.